Everything you were taught about Einstein and the speed of light is the safe version of the story. There is another version, the real one, and it has been sitting in plain sight since 1905, published in a German physics journal, written by a 26-year-old patent clerk who could not get a teaching job, a man with no laboratory, no university affiliation, no research funding, and no colleagues who understood what he was doing. He worked 6 days a week evaluating patent applications for electromagnetic devices at the Swiss Federal Patent Office in Bern, earning 3,500 Swiss francs a year. His title was Technical Expert, Third Class. That is not a joke. That was his actual job title. And in his spare time between patent applications and dinner with his wife Maileva, this man wrote a paper that destroyed time. Not figured out how fast light travels, not calculated a speed limit for the universe. He did something so much stranger than that, and I have spent an embarrassing number of hours trying to figure out why nobody told me what he actually did, until I went and read the original paper myself. Here is the version you were taught. Einstein discovered that the speed of light is constant, 186,000 miles per second. Nothing can go faster. E equals mc squared. Genius. Done. Here is what actually happened. Einstein did not discover that the speed of light is constant. He assumed it. He took it as a starting axiom, the same way you might assume the angles of a triangle add up to 180 degrees. And then he asked a very specific question. If the speed of light is truly the same for every observer, regardless of how fast they are moving, what does that require space and time to do? The answer broke everything. It required time to not be universal. It required now to not exist as a concept with any physical meaning. It required two people standing next to each other to disagree about the order of events happening billions of miles away, and for neither of them to be wrong. It required the future to be just as real as the past, already existing, already fixed, already there, waiting for your consciousness to crawl through it the way a needle moves across a record that has already been pressed. Einstein knew this. He knew it in 1905. And a few weeks before he died in 1955, he wrote something in a letter, just a single sentence, that physicists still do not fully know how to sit with. We will get to that sentence. But the fact that it exists, that it was written, and that it has been quietly acknowledged but never loudly discussed for 120 years, should tell you something about the nature of what was actually found. The question this video is built around is straightforward. If the speed of light was solved in 1905, why does nobody talk about what the solution actually means for whether time is real? And I want to be clear about something before we go any further. This is not fringe. This is not a thought experiment. This is not philosophical speculation that can be waved away by someone who prefers hard data. The implications I am going to walk you through have been confirmed by experiments repeatedly for over 100 years. They are confirmed every single day by the GPS satellite system in your phone. They were confirmed in 1971 by atomic clocks on commercial airline flights. They were confirmed in 2002 at a laboratory in Colorado by measuring time passing at different rates across a height difference of 1 millimeter. 1 millimeter. The precision of confirmation is now at 21 decimal places. And yet, if you ask the average physics graduate what special relativity says about whether the future already exists, you will get an uncomfortable pause. Not because they do not know, because they do not want to say it. So I will. The paper was called On the Electrodynamics of Moving Bodies. It was received by the journal Annalen der Physik on June 30th, 1905, and published on September 26th. It is 30 pages long. It contains no references, zero, not a single citation to another paper. Go check. I am not exaggerating. The most important physics paper of the 20th century does not reference a single other work. It mentions 5 scientists by name in the entire text: Newton, Maxwell, Hertz, Doppler, and Lorentz. That is it. I personally think this is the most underrated part of the story. Every scientific paper you have ever seen, every single one, exists in a web of citations. It references prior work, builds on established foundations, positions itself in a lineage of research. Einstein's paper does none of that. It reads like a man sitting alone in a room, working everything out from scratch. Because that is exactly what it was. And the circumstances of how this paper came to exist matter, because they tell you something about the institutional dynamics that shaped what happened to its implications afterward. Einstein had graduated from the Swiss Federal Polytechnic in Zurich in 1900, one of the weakest students in his class. He had alienated several professors, most notably Heinrich Weber, whose lectures Einstein found outdated, and Hermann Minkowski, whose mathematics lectures Einstein regularly skipped. Minkowski would later call him a lazy dog. Einstein applied for academic positions across Europe and was rejected by everyone. He could not even get a job as a high school teacher. His friend Marcel Grossman's father, who had connections at the patent office, eventually secured him the position in Bern. He started in June 1902. His intellectual companions during this period were thin. His wife Mileva Maric had studied physics alongside him at the Polytechnic and was herself talented, though the extent of her contribution to his work remains debated by historians. His closest friend was Michel Besso, a fellow patent office employee, an Italian-Swiss engineer, whom Einstein later described as someone he could not have found a better sounding board for in all of Europe. And there was the Olympia Academy, which was Einstein, Maurice Solovin, and Konrad Habicht, 3 friends in an apartment reading philosophy books and arguing about physics. That was the entire support structure behind the paper that rewrote the operating system of reality. Between March and September of 1905, working on his own time after patent office hours and on Sundays, Einstein produced 4 papers that each would have been career-defining for any physicist, plus a doctoral dissertation. His paper on the photoelectric effect, submitted in March, proposed that light consists of discrete quanta of energy, an idea so radical that even Planck rejected it for years. His paper on Brownian motion, submitted in May, provided theoretical proof that atoms exist at a time when many physicists still considered atoms a useful fiction. His follow-up paper in September derived E equals mc squared in 3 pages, and in between, submitted in June and published in September, the Relativity paper. Historians call 1905 Einstein's annus mirabilis, his miracle year. But what strikes me is that the miracle happened in total obscurity. Nobody in the physics establishment knew who this man was. Nobody was watching. The most productive burst of creative output in the history of science occurred in a patent office, after hours, by a man that the academic world had already decided was not worth hiring. There is something about this that I think matters for understanding what happened to the implications of his work. Einstein was not embedded in an institution. He did not have colleagues who could challenge him, mentor him, or temper his conclusions. He was not surrounded by the social pressures of academia, the unwritten rules about which questions are professionally safe to ask and which ones will get you labeled a crank. He was just a man in a room with the equations, and the equations told him something that nobody in a university position would have been brave enough or professionally reckless enough to publish. I think about this a lot. If Einstein had been a professor at Berlin or Göttingen, surrounded by senior colleagues who had spent their careers building on Newtonian mechanics, would he have published a paper that abolished absolute time? Or would the social pressure of the academy have filed down the edges? We will never know. But the fact that the most radical paper in physics came from outside the system is not, I think, a coincidence. It is a data point about how systems handle uncomfortable truths. And there is a personal detail from this period that I find almost painfully poignant. In May 1904, Einstein and Milleva's first son, Hans Albert, was born. So during the miracle year, Einstein was not just a patent clerk writing physics in his spare time. He was a new father. He was changing diapers and evaluating patents and rewriting the laws of the universe, all at the same time, in the same apartment in Bern, with no help and no indication that anyone would ever care about the papers he was producing. The image of a man feeding his infant son with one hand while scribbling equations about the nature of time with the other is not documented in any biography, but it is not hard to imagine, and it captures something essential about the distance between the significance of what was being created and the mundane conditions of its creation. And here is where the story starts going somewhere that every pop science video about Einstein avoids. The paper contains two postulates, just two. Everything that follows, every consequence, every implication that will haunt us for the rest of this video comes from these two starting assumptions. Postulate 1. The laws of physics are the same in all inertial reference frames. If you are in a spaceship moving at constant velocity or sitting still on Earth, there is no experiment you can do to determine which one of you is really moving. Physics works the same either way. This was not new. Galileo essentially said the same thing 300 years earlier. You can play ping pong on a smoothly moving train just as easily as on the ground. The laws of motion do not care. Postulate 2. The speed of light in empty space is always the same, regardless of the motion of the source that emitted it. If a flashlight on a train moving at half the speed of light fires a beam forward, that beam does not travel at 1.5 times the speed of light. It travels at exactly the speed of light, the same speed you would measure if the flashlight were sitting on a table. These two statements sound almost boring. They sound like reasonable starting points. But put them together and follow the logic rigorously, which is what Einstein did over the course of those 30 pages. And something terrifying falls out of the math. Because think about it, if the speed of light is always the same for every observer, but two observers are moving relative to each other, then something else has to give. They cannot both measure the same speed of light unless their measurements of space and time are different from each other. The speed of anything is just distance divided by time. If the speed is fixed, but the observers are in different states of motion, then either the distance is different for each of them, or the time is different, or both. Einstein showed that it is both. Time passes at different rates for observers in relative motion. This is time dilation. It is governed by the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus v squared over c squared. At 87% of the speed of light, gamma equals 2. A clock moving at that speed ticks at half the rate of a stationary clock. Not appears to tick slower, actually ticks slower. If your twin rockets away at 87% of c and comes back, they have aged half as much as you. This is not a thought experiment. This has been measured, but we will get to the measurements. And lengths contract. A meter stick moving past you at 87% of the speed of light measures only half a meter long. Not appears to be half a meter. Not looks like half a meter from your angle. Is half a meter as measured in your reference frame. The object has genuinely contracted along its direction of motion. But here is the result that Einstein himself put first in the paper, the one he spent the opening section developing before he derived anything else, the one that I think he considered the most fundamental of all the consequences. And it is the one that gets the least attention in every popular account of relativity I have ever seen. The relativity of simultaneity. Two events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first. And this is not about perception, not about reaction time, not about the finite speed of light reaching your eyes. This is about the structure of reality itself. There is no fact of the matter about whether two distant events happened at the same time. It depends on who is asking, and both answers are equally correct. Einstein gave this thought experiment in his 1917 popular book, Relativity, the special and general theory. Imagine a train moving at high speed. Lightning strikes both ends of the train at the same instant, as judged by someone standing on the platform exactly midway between the two strikes. The light from both strikes reaches the platform observer at the same time. She says the strikes were simultaneous. Fair enough. But the person sitting in the middle of the train is moving toward one strike and away from the other. Since the speed of light is the same in all directions in her frame, and she receives the light from the forward strike before the light from the rear strike, and she is equidistant from both ends of the train, she concludes the strikes were not simultaneous. The forward one happened first, and here is the part that every textbook states, but nobody dwells on long enough. Neither observer is wrong. There is no deeper truth about which observer has the real simultaneity. The universe does not have a preferred reference frame. There is no cosmic clock ticking in the background, establishing the true order of events. The relativity of simultaneity is not a quirk of measurement. It is not an artifact of communication delay. It is a feature of space-time itself. John D. Norton at the University of Pittsburgh, who has spent decades studying Einstein's original manuscripts, writes that this is the central adjustment Einstein made to our understanding of space and time. Once you grasp the relativity of simultaneity, everything else in special relativity makes sense. Until you grasp it, nothing quite makes sense. I have been obsessed with this specific result since I first properly understood it, because everything else follows from it. Time dilation follows from it. Length contraction follows from it. And the most disturbing implication of all, the one we are going to spend the rest of this video descending into, follows from it too. But the physics community in 1905 was not ready. After the paper was published on September 26th, Einstein waited. He checked subsequent issues of Annalen der Physik for responses, for citations, for any indication that someone had read what he wrote and understood its significance. Silence. Months of it. The first major physicist to take notice was Max Planck, who was co-editor of the journal, had actually read the paper carefully. By November 1905, just 2 months after publication, Planck gave a lecture about Einstein's theory at the University of Berlin. But Einstein did not know this was happening. He was still in Bern, still evaluating patterns, still waiting for any sign that the wider physics world had noticed. His first letter from a professional physicist did not arrive until March 1906. It was from Planck, and Einstein described it to his friend Solovine as filled with vibrant enthusiasm. He wrote on April 27, 1906, "My papers are much appreciated and are giving rise to further investigations. Professor Planck of Berlin has recently written to me about that." 1 letter, 6 months of silence, followed by 1 letter for the paper that destroyed absolute time. When Max von Laue traveled to Bern to meet Einstein later that year, he was so surprised to find a young man instead of a professor that he initially walked right past him. In April 1906, Einstein was promoted to technical expert second class with a salary of 4,500 francs for his patent work, not his physics. Without Planck's early championship, the theory might have languished for years. Even with it, broader acceptance came slowly. The first direct experimental confirmation of time dilation did not arrive until the Ives Stilwell experiments of 1938 through 1941, over 30 years after the paper was published. But something happened in between that made the implications inescapable. And the man who did it was the same professor whose mathematics lectures Einstein had skipped. Hermann Minkowski was born in 1864 in Alexotas, which is now part of Kaunas in Lithuania, but was then part of the Russian Empire. His family moved to Königsberg, Prussia, when he was 8, and he turned out to be a mathematical prodigy. He won the Grand Prix of the French Academy of Sciences at age 17, sharing it with the much older Henry Smith. By 1902, he was a professor at the University of Göttingen, the world capital of mathematics. He was a member of the same faculty as David Hilbert, Felix Klein, and other titans of early 20th century mathematics. He was, by any measure, a brilliant mathematician operating at the highest level of the discipline, and he had been following his former student's paper with growing interest. Remember, Minkowski had taught Einstein at the Polytechnic. He knew Einstein was smart but undisciplined. He had called him a lazy dog, and now this lazy dog had produced a theory that the entire physics world was struggling to absorb. Minkowski read the 1905 paper and saw something in the equations that Einstein himself had not fully articulated. Einstein had presented his results kinematically as algebraic relationships between measurements made by observers in relative motion. What Minkowski saw was something deeper. He saw geometry. On September 21st, 1908, at the 80th Assembly of German Natural Scientists and Physicians in Cologne, Minkowski delivered a lecture that would transform physics permanently. The opening lines are some of the most dramatic ever spoken at a scientific conference, and I want you to hear them exactly as he said them, because the phrasing matters. The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space by itself and time by itself are doomed to fade away into mere shadows. This was not a poet. This was not a philosopher making metaphorical gestures. This was a mathematician standing before a room full of physicists, telling them that Einstein's equations demanded the complete abandonment of space and time as separate entities. What exists, what is real, what has independent existence, is not space plus time. It is space-time, a single four-dimensional geometric object in which time is a dimension exactly as real and exactly as static as the three spatial dimensions. And in that geometry, the future is not something that has not happened yet. The future is a place, a region of the four-dimensional block, already there, already fixed, waiting for nothing, because waiting is something that happens in time, and the block does not exist in time. The block is time. Einstein's initial reaction, he called it superfluous learnedness. He dismissed Minkowski's geometric reformulation as unnecessary mathematical decoration, adding nothing to the physics that the algebraic equations did not already contain. The original approach worked fine for making predictions. Why dress it up in four-dimensional geometry? This is one of those moments in the history of science that I find genuinely tragic, because Minkowski never got to see how wrong Einstein was about this dismissal. On January 12, 1909, less than 4 months after delivering that Cologne lecture, Hermann Minkowski died of a ruptured appendix. He was 44 years old. According to reports, his last words were, "What a pity that I have to die in the age of development of relativity." He had published the lecture in Physikalische Zeitschrift, sending the manuscript to the editor on December 23, 1908, but he never saw its full impact on physics. And here is the turn that makes Minkowski's death more than just sad. Einstein dismissed his geometry, but by 1912, when Einstein was struggling to extend special relativity to include gravity to build what would become general relativity, he realized he needed advanced mathematics he did not possess. He needed tensor calculus. He needed differential geometry. He needed a way to describe curved spacetime. And all of these required exactly what Minkowski had built, a four-dimensional geometric framework in which time is a genuine dimension. Einstein went to his friend Marcel Grossmann, the same friend whose father had gotten him the patent office job, and reportedly said, "Grossmann, you have got to help me or I will go crazy." Grossmann pointed him to the Ricci calculus, the mathematical language of curved manifolds. Einstein later confessed, "I have gained great respect for mathematics, whose more subtle parts I considered until now, in my ignorance, as pure luxury." He also acknowledged explicitly that Minkowski's formulation made general relativity possible. The framework Einstein called superfluous learnedness in 1908 became the foundation of the field equations he published in November 1915. The field equations that predicted gravitational waves, confirmed in 2015 by LIGO. The field equations that predicted black holes, imaged in 2019 by the Event Horizon Telescope. The field equations that describe the expansion of the universe, the bending of light around massive objects, the GPS corrections in your phone. All of it built on the four-dimensional spacetime that Minkowski imagined and Einstein initially rejected. And all of it carrying the same passenger that Minkowski's geometry implies and that Einstein eventually accepted. The block universe, the elimination of flow, the reality of the future. Because in Minkowski spacetime, there is no mechanism for time to pass. The block simply exists. Different observers cut different three-dimensional slices through it, and each slice is a different now, and no slice is privileged. The experience of moving through time is not described by the physics. The physics describes the block. Your consciousness does something that the block does not require, and nobody knows what that something is. I want to stop here for a moment and make sure the weight of this lands properly, because it is easy to let four-dimensional geometry sound like an abstraction that has nothing to do with your actual life. What Minkowski spacetime means, in concrete terms, is this. The room you are sitting in right now exists as a four-dimensional object. It has length, width, height, and duration. The version of the room with you in it right now, reading these words or listening to them, is one three-dimensional cross-section of that four-dimensional object. The version of the room from yesterday, with you not in it, is another cross-section. The version of the room from tomorrow is another. And all of these cross-sections exist. Not existed, not will exist. Exist. Present tense. They are all equally real parts of the same four-dimensional object. This is not a metaphor. This is what the geometry says. And the geometry has been confirmed to 21 decimal places. Now you might say that is just a mathematical description. The map is not the territory. The fact that you can draw a four-dimensional coordinate system does not mean the universe is actually a four-dimensional block. Maybe the math is just a useful tool, and the real universe does unfold over time in the way you experience it. This is a reasonable objection. It is the objection Lee Smolin makes. It is the objection philosophers of science have been raising for decades, but it runs into a problem. The math does not merely describe the measurements. The math makes predictions that require the four-dimensional description to be taken seriously. Time dilation is not just a mathematical convenience. It is a physical fact. Clocks rarely do tick at different rates depending on their motion. Muons really do live longer when they are moving fast. GPS really does fail if you do not correct for the curvature of space-time. These are not features of the map. They are features of the territory. And the territory, as best we can measure it, has four dimensions. Hermann Weyl, one of the great mathematicians of the 20th century, captured this in a passage from his 1949 book, Philosophy of Mathematics and Natural Science, that I think is the most haunting single paragraph ever written about the nature of time. He wrote, "The objective world simply is. It does not happen. Only to the gaze of my consciousness crawling along the lifeline of my body does a section of this world come to life as a fleeting image in space which continuously changes in time. The objective world simply is. It does not happen. Your consciousness crawls along your lifeline. The world does not move. You do, or rather, you experience the illusion of movement through something that is not moving. But I am getting ahead of myself, because before we confront the block universe directly, I need to show you the argument that turned an implication into something approaching a proof. And the argument is, I personally think, the single most unsettling thought experiment in all of physics. More unsettling than Schrödinger's cat, more unsettling than the double-slit experiment, more unsettling than anything in quantum mechanics. Because quantum mechanics, at least, has the decency to be weird only at small scales. This argument works at the scale of two people walking down a street. In 1966, a Dutch physicist named C.W. Reed Dijk published a paper in the journal Philosophy of Science titled "A Rigorous Proof of Determinism Derived from the Special Theory of Relativity." The title alone should give you pause. The following year, the philosopher Hilary Putnam at Harvard published an independent version in the Journal of Philosophy titled "Time and Physical Geometry." But it was the physicist Roger Penrose who gave the argument the image that makes it impossible to forget. He presented it in his 1989 book, The Emperor's New Mind, and it is now known as the Andromeda paradox. Here is the setup. Two people pass each other on a street. One is walking north, the other south. They are moving relative to each other at about 1 meter per second. Completely ordinary, an event that happens 1 million times a day in every city on Earth. Now, because they are in relative motion, the relativity of simultaneity applies to them. Their planes of simultaneity, their definitions of now, are tilted relative to each other. For events close by, the tilt is imperceptibly small. You would need instruments far beyond human perception to detect it. But the amount of tilt grows with distance. For very distant events, the disagreement about now becomes large. The Andromeda galaxy is about 2.5 million light years from Earth. For two people walking past each other at 1 meter per second of relative velocity, the formula gives a time shift of approximately v times d divided by c squared. Plug in the numbers. The difference in what they would call now on the Andromeda galaxy is roughly 3 days. 3 days from a walking pace. One of them, right now, in their present moment, is simultaneous with Tuesday on Andromeda. The other, right now, in their present moment, is simultaneous with Friday on Andromeda. And if the Andromeda galaxy happened to contain a civilization making a decision, say whether to launch an invasion fleet toward Earth, then one of these two people on the street is living in a present where the decision has not yet been made. The other is living in a present where the fleet has already launched. 3 days of Andromedan history hang in the balance of a walking pace. Penrose wrote, "Two people pass each other on the street, and according to one of the two people, an Andromedan space fleet has already set off on its journey, while to the other, the decision as to whether or not the journey will actually take place has not yet been made." How can there still be some uncertainty as to the outcome of that decision? If to either person the decision has already been made, then surely there cannot be any uncertainty. The launching of the space fleet is an inevitability. This is not about observation. Neither person can see what is happening on Andromeda in real time. The light takes 2.5 million years. The argument is about what is real. If there exists a valid reference frame in which the fleet has launched, and both reference frames are equally valid descriptions of reality, then the launch is real. It has happened. It exists. The future, at least that particular piece of it, is not open. It is settled. Brian Greene at Columbia University pushed the numbers further. Consider an alien sitting on a planet 10 billion light years away from Earth. If that alien starts walking toward Earth at about 10 miles per hour, the tilt of their simultaneity plane relative to yours shifts their now on Earth by approximately 149 years into our future. A casual stroll, 10 miles per hour, and their reference frame is no less valid than yours. If their present moment contains events 149 years in your future, then those events are real. They exist. They are as fixed as anything in the past. I need to pause here because I think the sheer strangeness of this gets lost in the numbers. What this means is that the reality of the future is not an abstract philosophical claim. It is a mathematical consequence of two people moving at different speeds. You and your neighbor walking in different directions on the same street are living in different presents. The difference is unmeasurably small for anything local, fractions of a nanosecond for events in the next room. But the effect scales with distance, and the universe is very, very large. At cosmological distances, the disagreement about now becomes years, decades, centuries. And no frame of reference is special. No frame has the right now. They are all equally valid. This is not a limitation of measurement or knowledge. It is the structure of reality. Reerdijk's conclusion was clinical. There does not exist an event that is not already in the past for some possible distant observer. Putnam's was more direct. Any future event is already real. And then Putnam added a line that I genuinely think about more often than is healthy for a person making YouTube videos. Aristotle was wrong. At least he was wrong if relativity is right. That line has stayed with me since I first read it. Because what Putnam is saying is not that Aristotle made a small mistake about some technical detail. He is saying that the most fundamental intuition that every human being has ever had about the nature of reality, that the future is open and the past is closed, that what has not yet happened is different in kind from what has already happened, is wrong. Not philosophically wrong, physically wrong. Wrong in the same way that the earth is flat is wrong. A useful approximation for everyday life that completely fails to describe what is actually going on. Now, I need to be honest here, because intellectual honesty matters more than a clean narrative, and this audience will fact-check me. There are serious criticisms of the Reerdijk-Putnam argument. The most important comes from philosopher Howard Stein, who published a paper in Philosophy of Science in 1991 titled On Relativity Theory and Openness of the Future. Stein proved mathematically that the argument relies on a specific and contestable assumption that the boundary between real and not yet real must be a global plane of simultaneity. In other words, Reerdijk and Putnam assumed that exists now must mean everything on my simultaneity plane exists now. Stein showed that you can define a local notion of becoming restricted to events within your past light cone. And this local becoming is perfectly compatible with Minkowski spacetime without requiring the block universe. Other critics point out that neither observer can actually observe the 3-day discrepancy on Andromeda, since the light takes 2.5 million years. So the disagreement concerns coordinate assignments, mathematical labels, not physically measurable outcomes. The events on Andromeda are space-like, separated from both observers, which means neither event is in either observer's causal past or causal future. Drawing conclusions about what is real from space-like separated coordinate assignments may be overstepping what the physics actually says. These are legitimate objections. I take them seriously. They prevent me from saying, flatly, the Reerdijk-Putnam argument proves the block universe. It does not prove it in the way a mathematical theorem is proved. But notice what even the critics are not disputing. They are not disputing the relativity of simultaneity itself. They are not disputing that now is observer-dependent. They are not disputing that the mathematics of special relativity is incompatible with a single universal present moment that divides reality into a fixed past and an open future. What they are disputing is whether this forces you to accept the strongest version of eternalism, where every future event is as real and as fixed as every past event. The weaker conclusion, the one that even the critics accept, is disturbing enough on its own. There is no universal now. The present moment you are experiencing has no special status in the physics. The flowing river of time, the sense that the past is gone and the future is open, has no counterpart in the equations. That is not debated. That is what the equations require. And the equations have been verified to extraordinary precision. Speaking of which, let me talk about the speed of light itself for a moment, because there is a misconception here that I think changes the entire picture. And it is the kind of thing where once you see it, you cannot unsee it. The speed of light is not about light. I know that sounds like a contradiction. The phrase speed of light has the word light right in it. But follow the logic. You can derive the entire Lorentz transformation, the full mathematical structure of special relativity, from three assumptions that never mention light. First, no preferred inertial frame. Second, space is homogeneous and isotropic, meaning it looks the same everywhere and in every direction. Third, velocities compose in a consistent way. Make those three assumptions, work through the algebra, and a maximum speed falls out of the equations. A speed baked into the geometry of space-time itself. A speed that would exist even if photons did not. Light happens to travel at this speed because photons have zero mass, and massless particles are required by the equations to travel at the maximum space-time speed. But the speed itself is not a property of light. It is a property of the fabric of reality. It is the rate at which one event can causally influence another. The astrophysicist Matt O'Dowd put it simply: space-time could not care less about light. The cosmic speed limit is about something much deeper. Some physicists have started calling it the speed of causality rather than the speed of light. The constant c appears in the Minkowski metric, the equation that defines the geometry of space-time. ds squared equals c squared dt squared minus dx squared minus dy squared minus dz squared. It is the conversion factor between space and time. It defines the light cone structure, which determines what can influence what. It is not a speed limit imposed on objects from outside, like a speed limit on a highway. It is a structural property of the road itself. You cannot exceed it because the road does not go there. And this leads to one of the most beautiful and unsettling ideas in physics. I actually first encountered this in a Brian Greene lecture years ago, and it genuinely rewired how I think about everything that followed. Everything in the universe is always moving through space-time at the speed of light, not through space, through space-time. There is a quantity in relativity called the four-velocity, which combines your motion through space and your motion through time into a single four-dimensional vector. And the magnitude of that vector is always exactly c. Always. For everything. For you sitting in your chair right now. For a speeding bullet. For a muon created in the upper atmosphere. For a photon from a distant star. If you are sitting perfectly still, not moving through space at all, then all of your motion through space-time is directed through time. You are hurtling through time at the maximum rate. Your clock ticks as fast as it can possibly tick. But if you start moving through space, some of your space-time velocity gets redirected from the time direction to the space direction. You move faster through space, and therefore you move slower through time. This is time dilation, not as a strange consequence of an abstract theory, but as a geometric redistribution of motion through four dimensions. The math is simple. your speed through space squared plus your speed through time squared equals c squared. Pythagoras in 4 dimensions. And it means that the faster you go through space, the slower you must go through time, because the total has to stay constant at c. At the speed of light through space, all of your space-time motion is directed through space. None is left for time. Time stops completely. This is why nothing with mass can reach the speed of light. It would require all of your motion through time to be converted into motion through space. You would have to stop moving through time entirely. And the equations say achieving this requires infinite energy for anything with mass. Photons, being massless, do it. They travel at c through space, which means they have zero motion through time. From the perspective of a photon, if such a perspective could meaningfully exist, and technically it cannot, because you cannot construct a valid reference frame for a massless particle. But bear with the thought experiment for a moment. No time passes. Zero. The universe, in the photon's direction of travel, has zero spatial extent. A photon emitted by a star 8 billion light years away and absorbed by your retina has, from its own frame, existed for exactly 0 seconds. Its emission and its absorption are, from its perspective, the same event. I realize this is the kind of thing where you need to just sit with it. The light entering your eyes right now, from the screen, from the room around you, has never experienced time. It never will. From light's perspective, the entire history of the universe, 13.8 billion years of it, is a single frozen instant. Now someone is going to point out in the comments, correctly, that speaking of a photon's perspective is not technically rigorous. You cannot Lorentz boost to the speed of light. The transformation is undefined there. That is fair. Brian Greene himself acknowledges this as a pedagogical heuristic, not a literal description. Several physicists have noted that the 4-velocity normalization to c, while mathematically precise, does not straightforwardly mean everything moves at c in the way it sounds in English. I accept those caveats, but the underlying physics is unambiguous. Time dilation is real. The faster you move through space, the slower your clocks tick. At the speed of light, the dilation factor is infinite, and the clock stops. Whether you describe this as all motion is through time when stationary, or in more technical 4-vector language, the physical consequence is the same. Time is not a river flowing at a fixed rate. It is a dimension, and your experience of its passage depends on how you are moving through the other dimensions. And here is why this matters for the question we are building toward. If time is a direction, not a river, then the block universe is not some exotic philosophical addition to the physics. It is the physics. You are not being carried along by time. You are oriented in it. Your consciousness processes one direction of a 4-dimensional geometry and calls it the passage of time. But the geometry does not flow. The geometry just is. Maybe you are thinking, okay, this is all very clever mathematically, but does any of it actually show up in the real world? Is this just formalism, or does the universe genuinely behave this way? It behaves this way. The proof is so pervasive that you carry it in your pocket. Every GPS satellite orbiting Earth is a functioning time dilation laboratory. There are about 31 of them, circling at roughly 20,200 kilometers altitude, moving at about 3.87 kilometers per second. At that orbital speed, special relativistic time dilation causes their onboard atomic clocks to lose approximately 7.2 microseconds per day compared to clocks on the ground. The clocks in orbit tick slower because they are moving through space, which means they are moving through time at a slightly reduced rate. But there is a competing effect. The satellites are also higher in Earth's gravitational field, farther from the center of Earth's mass. General relativity, the extension of special relativity to include gravity that Einstein published in 1915, predicts that clocks in weaker gravitational fields tick faster. This gravitational time dilation adds approximately 45.9 microseconds per day to the satellite clocks. The net effect is that satellite clocks run about 38.6 microseconds per day fast. Roughly 38 microseconds gained minus roughly 7 microseconds lost equals roughly 38.6 microseconds per day ahead of ground clocks. 38 microseconds sounds tiny. It sounds like nothing. Here is why it matters. Light travels about 11.5 kilometers in 38 microseconds. If GPS did not correct for relativistic time dilation, your position on the map would drift by approximately 10 kilometers every single day. Within a week, GPS would place you in the next city. Within a month, the wrong country. The system would be functionally useless. Before any GPS satellite is launched, its clock frequency is pre-adjusted. The nominal oscillation frequency is 10.23 gigahertz, but the clocks are actually set to run at 10.229,999,9543 gigahertz, a tiny, precise offset that exactly compensates for the fact that time passes at a different rate in orbit than it does on the surface of the Earth. Every time you open a map app on your phone, every time your navigation tells you to turn left in 200 meters, it is silently, invisibly correcting for the fact that Einstein was right about time in 1905. The correction factor comes directly from the equations in that 30-page paper with 0 references. This is not theoretical anymore. This is infrastructure. The satellites do not directly demonstrate that two clocks in different states of motion will disagree when you bring them back together. What about a direct test? What about physically taking clocks, separating them, moving them differently, and seeing if they show different times when reunited? That was done in October 1971 by Joseph Hafele and Richard Keating, and their experiment is one of my favorite stories in all of physics, partly because of the science, and partly because of how hilariously low budget it was. Hafele was a physicist at Washington University in St. Louis. Keating was an astronomer at the United States Naval Observatory. They secured a grant from the Office of Naval Research. For $8,000, they obtained 4 cesium beam atomic clocks. And then they did something nobody had done before. They bought commercial airline tickets, put the clocks on airplanes, and flew them around the world. Not charter flights, not military aircraft, commercial airliners. They bought 2 seats per flight, one for the scientist accompanying the clocks and one for the clock itself. The clocks were literally strapped into passenger seats. The ticket was purchased in the name Mr. Clock. This is documented. The total cost of the airline tickets was about $7,600 out of the $8,000 budget. They flew eastward around the world first, then westward, then brought the clocks back to the Naval Observatory and compared them to reference clocks that had stayed on the ground. The results were published in the journal Science on July 14, 1972, in 2 back-to-back papers. For the eastward trip, The airborne clocks lost 59 nanoseconds, plus or minus 10, compared to the ground clocks. The theoretical prediction from relativity was a loss of 40 nanoseconds, plus or minus 23. For the westward trip, the airborne clocks gained 273 nanoseconds, plus or minus 7. The prediction was a gain of 275, plus or minus 21. The asymmetry between east and west is important and instructive. Eastward flying clocks are moving in the same direction as Earth's rotation, so their total velocity relative to the non-rotating center of Earth frame is higher. Airplane speed plus Earth's rotation speed. More speed means more time dilation, means more time lost. Westward flying clocks are opposing Earth's rotation, so their net velocity is lower, producing less time dilation. Meanwhile, the gravitational effect from altitude makes clocks gain time in both directions. The interplay between these effects produces the asymmetry. Those clocks came back disagreeing about how much time had passed, not because they malfunctioned, not because of vibration or temperature or instrument error, because time actually passed at different rates depending on their motion through spacetime. $8,000 and some commercial airline tickets confirmed what a patent clerk derived from two postulates in 1905. But even Hafel Keating was crude by later standards. In 1977, the CERN muon storage ring experiment measured time dilation for muons circling a ring at 99.94% of the speed of light. At that speed, the Lorentz factor gamma equals approximately 29.33. The muon's rest frame lifetime is 2.2 microseconds. CERN measured dilated lifetimes of 64.4 microseconds. Agreement with Einstein's prediction, within 2 parts per thousand. And these muons were experiencing accelerations of approximately 10 to the 18th g, a billion times the force of gravity at Earth's surface. Acceleration that would crush atoms. And time dilation held perfectly. Cosmic ray muons give you an even more visceral demonstration. When high-energy particles from deep space slam into atoms in the upper atmosphere at about 10 to 20 kilometers altitude, they create showers of secondary particles, including muons. A muon at rest decays in about 2.2 microseconds. Even traveling at 99.8% of the speed of light, it should only cover about 660 meters before decaying. It should never make it to the ground. But muons are abundantly detected at sea level. Thousands of them are passing through your body right now as you listen to this. The Rossi Hall experiment first confirmed this in 1941. Frisch and Smith measured a dilation factor of about 8.4 on Mount Washington in 1963. The muons survive because their clocks are running slow relative to ours. From the muon's perspective, it is the distance to the ground that has contracted, not its lifetime that has expanded. Both descriptions are correct. Both are the same physics seen from different frames. And then there is the measurement that I think should have been front-page news everywhere and was barely covered. In February 2022, Junier's group at JILA, a joint institute between the University of Colorado and NIST in Boulder, published a paper in Nature. They measured gravitational time dilation across a height difference of 1 millimeter, not 1 kilometer, not 1 meter, 1 millimeter. Using about 100,000 ultra-cold strontium atoms trapped in an optical lattice, they achieved a fractional frequency uncertainty of 7.6 times 10 to the negative 21. That is 21 decimal places of precision, enough to detect that the top of a 1 millimeter column of atoms is aging by a fantastically tiny amount, faster than the bottom. Time runs at a different rate across the height of a grain of rice. That is not a theoretical prediction. That is a measurement, published, verified. And in 22,004, they pushed to the sub-millimeter scale. NIST has plans for an optical lattice clock to be driven to the summit of Mount Blue Sky in Colorado for comparison with a lab clock at lower altitude. And 2 clocks are planned for the International Space Station that would test time dilation 50 times more stringently than any previous experiment. The universe is not hedging. Every experiment at every scale, from satellite orbits to subatomic particles to strontium atoms separated by less than a millimeter, confirms the same result. Time is not fixed. Time is not universal. Time depends on how you are moving and where you are in a gravitational field. And the framework that predicted all of this was written down by a man whose employer did not think he was qualified to be a professor. But here is where I need to shift the question from, is this true, to, why don't you already know this? Because the experiments are not the problem. The experiments are unimpeachable. The problem is what happens when you follow the thread to its logical conclusion and look around for someone in a position of authority willing to state that conclusion publicly. I spent a long time trying to understand why this particular implication of relativity is so absent from popular science. Time dilation is everywhere. Length contraction gets a mention. E equals mc squared is on t-shirts. But the block universe, the elimination of now, the argument that the future already exists, these are treated as exotic philosophical footnotes rather than what they actually are. The central implications of the central theory. Go to any popular science channel, watch any documentary about Einstein, read any high school or even college physics textbook. What will you find? Time dilation, length contraction, E equals mc squared, the train thought experiment. Maybe nothing can go faster than light. Those are the safe talking points, the parts of relativity that are strange but not threatening. What you will not find, or will find only with heavy hedging and qualifications, and some physicists believe disclaimers, is this: there is no universal now. The future is as real as the past. Free will, as normally understood, is incompatible with the most natural reading of the most precisely confirmed theory in physics. Your experience of time flowing is a feature of your neurology, not a feature of reality. These are not obscure topics. They follow directly from the theory. They are discussed at every major conference on the foundations of physics. They have been published in peer-reviewed journals for over 75 years, and they are almost completely absent from public science communication. I have a theory about why, and it connects everything we have discussed. The reason is the same reason the Nobel Committee refused to honor relativity. The same reason Bergson's philosophical challenge was dismissed in a single sentence. The same reason physics textbooks teach the Lorentz transformation without mentioning what it implies about whether time flows. The implication is unbearable. Einstein should have received the Nobel Prize for Relativity. He never did. He received the 1921 Nobel Prize in Physics, actually awarded to him in 1922, and the citation read, "For his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect." The award notification telegram included a line unprecedented in Nobel history. Without taking into account the value that will be awarded your relativity and gravitation theories after these are confirmed in the future. They explicitly excluded his greatest achievement from the honor. This qualifying language has never appeared in any other Nobel Prize, before or since. The central obstacle was Alvar Gullstrand, a Swedish ophthalmologist who sat on the Nobel Physics Committee. Gullstrand was himself a Nobel laureate, winner of the 1911 prize in physiology or medicine for his work on optical properties of the eye. He was brilliant in his domain. He was not a physicist. He wrote a 50-page report in 1921, concluding that Einstein's relativity theories were devoid of any real content and bore no relationship with physical reality. Historian Robert Mark Friedman discovered from a Swedish mathematician's diary that Gullstrand once declared, "Einstein must never receive a Nobel Prize, even if the whole world demands it." Other committee members were no better equipped. Bernhard Hasselberg and Karlheim Jelenskiold simply could not follow the mathematics. Their documented objections included the claim that the effects of special relativity that can be physically measured are so small that they fall within the limits of experimental error. In 1921, for a theory that is now confirmed to 21 decimal places. And there was a darker force at work. On August 24th, 1920, a group calling itself the Working Society of German Scientists for the Preservation of Pure Science held a rally at the Berlin Philharmonic. Anti-Semitic pamphlets were handed out. Swastika lapel pins were sold at the door. Paul Wayland and Ernst Gerke accused Einstein of plagiarism and fraud from the stage. Nobel laureate Philipp Lenard attacked relativity publicly, arguing it violated healthy common sense. Lenard eventually co-authored the 4-volume Deutsche Physik textbook in 1936 and 37, which attempted to systematically purge Jewish contributions from German physics. Another Nobel laureate, Johannes Stark, joined him. Friedman argues, with extensive archival evidence, that committee members Arrhenius and Gullstrand incorporated arguments originating from these politically and racially motivated critics into their evaluations. The line between scientific skepticism and anti-Semitic prejudice was blurred, and nobody on the committee had the physics training to tell the difference. The compromise that eventually got Einstein a Nobel was engineered by physicist C.W. Oseen, who nominated Einstein specifically for the discovery of the law of the photoelectric effect, framing it as an empirical law of nature rather than a speculative theory. This bypassed the committee's allergic reaction to theoretical physics. And then Einstein did something that still makes me smile every time I think about it. When he delivered his Nobel lecture on July 11, 1923, in Gothenburg, he did not talk about the photoelectric effect. He talked about relativity. For the entire lecture, he used the platform they gave him for the lesser achievement to discuss the greater one that they had refused to honor. The Nobel Foundation had to add a footnote to the published lecture. The lecture was not delivered on the occasion of the Nobel Prize award and did not, therefore, concern the discovery of the photoelectric effect. The prize money, by the way, went to his ex-wife Mileva Maric, per their divorce settlement agreement. Einstein had promised her the Nobel Prize money before he had even received it. He was apparently confident enough in his work, just not in his committee. But the Nobel snub was just one front in the broader failure to reckon with what the equations actually said. There was a more direct confrontation about the nature of time itself, and it happened in Paris, and it was devastating. On April 6, 1922, at the Société Française de Philosophie Henri Bergson rose to challenge Einstein's interpretation of time. Bergson was not a fringe figure. He was arguably the most famous philosopher alive, winner of the 1927 Nobel Prize in Literature. His 1913 lecture in Manhattan was so oversubscribed that it caused what newspapers called Broadway's first ever traffic jam. He was president of the League of Nations Commission for Intellectual Cooperation. Huge figure. Bergson accepted the physics of relativity. He did not dispute a single equation. What he disputed was the philosophical conclusion Einstein drew from those equations. Bergson distinguished between two kinds of time. The first he called clock time, the spatialized, quantifiable, measurable time of physics, time as a fourth coordinate on a graph. The second he called duration, the lived, qualitative, flowing experience of time as felt by a conscious being. Memory, anticipation, the sense of one moment giving way to the next. Bergson argued these were different things and that Einstein was committing a philosophical error by equating one with the other, by declaring that physics has the final word on the nature of time. Einstein was, in Bergson's phrase, grafting a metaphysics onto science. Einstein's response lasted about a minute. It was one of the most efficient demolitions in intellectual history. There is no such thing as a philosopher's time. There is only a psychological time, different from the time of the physicist. That was it. The entire Western philosophical tradition of investigating the nature of time, from Aristotle, through Augustine, through Kant, through Bergson himself, dismissed as psychology. Not wrong, exactly, just irrelevant to the actual nature of reality. Bergson had made a technical error in his analysis of the twin paradox in a book he had written about relativity. It was a genuine mistake in the physics, and this error was weaponized to discredit his entire philosophical critique, which was deeply unfair because the core of Bergson's argument was not about the twin paradox. It was about whether physics has the right to declare that the lived experience of the present moment is an illusion. That is a philosophical question, not a physics question. And Einstein answered it with a physics answer. Historian Jimena Canales documented the aftermath in her 2015 book, The Physicist and the Philosopher, published by Princeton. She argues that this single confrontation shaped the institutional boundary between physics and philosophy for the next century. After 1922, physicists stopped engaging with philosophers about time. Philosophers stopped trying to challenge physics about time. And the question Bergson was really asking, the good question buried inside his flawed technical analysis, went unanswered. What was the question? If physics says the present moment is not special, but you are experiencing a present moment right now, which one is wrong? The physics or the experience? Einstein said, the experience, and physics largely followed him. But here is the thing about Bergson that the standard telling of this story leaves out. Two later Nobel laureates partially vindicated his position. Louis de Broglie argued that Bergson's philosophy foreshadowed certain concepts in quantum physics, and Ilya Prigogine, who won the Nobel in Chemistry in 1977 for his work on non-equilibrium thermodynamics, claimed that his results were close to the views expressed by Bergson and Whitehead. The arrow of time, the irreversibility of physical processes, entropy increase. These are features of physics that do seem to distinguish past from future in a way that special relativity alone does not. The debate is genuinely alive. I want to be explicit about this. The block universe is the most natural reading of the equations of special relativity and general relativity. It is not the only reading. Lee Smolin at the Perimeter Institute published Time Reborn in 2013, arguing passionately that the passage of time is real, that the present moment is special, and that the block universe confuses mathematical models, which are by nature timeless abstractions, with the physical reality they describe. Smolin argues that the very success of physics in describing the world as timeless mathematical structures has seduced physicists into believing that the structures are more real than the world they describe. The map has been confused with the territory. This is a genuinely compelling argument, and I went back and forth on it for days while researching this. Carlo Rovelli at Aix-Marseille University, author of The Order of Time, has pushed back against eternalism from a different angle. He has written that the block universe is an absurd position because the four-dimensional space-time of relativistic theories is a manifold of events, namely of happenings, and there is nothing static about them. Rovelli's view is more radical than either presentism or eternalism. He argues that time, at the most fundamental level, does not exist at all, not as a flow and not as a dimension, but that something like time emerges from deeper relational structures at the macroscopic level. Time is real in the way that temperature is real, not a fundamental property of individual particles, but a statistical property of large collections. Tim Maudlin at NYU has argued forcefully that nothing in Einstein's theory actually requires the block universe interpretation. The physics is about the geometry of space-time and the behavior of clocks and rulers. It does not, Maudlin insists, make any claim about whether the future is real in a metaphysical sense. Drawing that conclusion requires additional philosophical assumptions that go beyond what the equations state. George Ellis at the University of Cape Town has proposed what he calls the evolving block universe, a middle path where space-time is real and four-dimensional but grows over time. The past is fixed, already crystallized into definite events. The future is genuinely open, not yet determined. The present is the boundary, the growing edge, where quantum possibilities collapse into classical actualities. This preserves the four-dimensional geometry of relativity while rescuing the openness of the future. These are serious positions from serious people. I do not dismiss them. If anything, the fact that this debate is still active over a century after Einstein's paper should tell you something about how uncomfortable the block universe makes even professional physicists. But then there is the other side, and the other side speaks with a confidence that the critics rarely match. Sean Carroll at Johns Hopkins: the past and future are equally real. This is not completely accepted, but it should be. Brian Greene at Columbia: just the way an entire movie exists on a reel of celluloid, think of all moments of time as already existing too. The difference is that in the movies, a projector lights up each frame, but there is nothing in the laws of physics that selects one moment over another. And Max Tegmark at MIT, who provided the image that I cannot get out of my head, and that by the end of this sentence, you will not be able to get out of yours. You are a pattern in space-time, a mathematical pattern. Specifically, you are a braid in space-time. Indeed, one of the most elaborate braids known. A braid, static, fixed, woven into the four-dimensional fabric, not moving through time, existing in it. The way a figure woven into a tapestry exists in the fabric. The tapestry is not unrolling, The figure is not moving. The tapestry is already complete. What you experience as the unrolling is something your consciousness does, something your brain constructs, and nobody on either side of this debate can explain why. Because the deepest open problem is not whether the block universe is true. It is why, if the block universe is true, you experience anything at all. If you are a static four-dimensional pattern, what generates the experience of moving through time? In a movie, there is a projector. In the block universe, what plays the role of the projector? Michael Silberstein posed this question in a 2023 paper in Frontiers in Human Neuroscience. His answer was that nobody knows. The question does not even have a framework for generating candidate answers. It may be harder than quantum gravity, harder than the origin of consciousness itself, because it sits at the intersection of the two hardest problems in all of science, the nature of time and the nature of experience. Bratsko, a philosopher at MIT, put the strangeness in terms I find unavoidable. The block universe theory says you are spread out in time, something like the way you are spread out in space. And then, the future is a place just like Australia. Australia is far away spatially, and the future is also far away temporally. You do not think of Australia as less real because you are not currently there. It exists right now with its people and cities and coastlines, regardless of whether you observe it. The block universe says next Tuesday exists in the same way. Next year exists in the same way. The moment of your death exists in the same way. Not approaching, not waiting, just there. A point in the geometry. The question is not whether it is there. The math says it is there. The question is why you cannot see it from here. And this brings me to the sentence, the one I mentioned at the beginning, the one Einstein wrote at the end of his life. But first I need to tell you about the friendship that produced the final piece of this puzzle, because it is one of the strangest and most moving relationships in the history of science. By the late 1940s, Einstein had been at the Institute for Advanced Study in Princeton, New Jersey for about 15 years. He was in his late 60s, the most famous scientist in the world, largely isolated from the mainstream of physics, which had moved on to quantum mechanics and nuclear physics, while Einstein continued his lonely search for a unified field theory. Most of his younger colleagues considered this search a dead end. Einstein was aware of this. He did not care. His closest companion at the Institute was Kurt Godel, who had arrived in 1940 after a harrowing escape from Nazi-occupied Austria via the Trans-Siberian Railway through Japan and across the Pacific. Godel was 34 years younger than Einstein. He was thin, paranoid about his health, and ate almost nothing because he feared being poisoned, a fear that would eventually contribute to his death by self-starvation in 1978. He was also, by the consensus of virtually every logician and mathematician who has studied his work, the most important logician since Aristotle. The two men walked to work together almost every day at the Institute. Oscar Morgenstern, the economist, noted that Einstein once confided that his own work no longer amounted to much, and that he came to the Institute mainly for the privilege of walking home with Godel. Whether this was modest deflection or genuine sentiment, the image is striking. The greatest physicist and the greatest logician of the century, walking together through the streets of Princeton, discussing the nature of time. And in 1949, Godel gave Einstein a birthday present, a proof that time does not exist. On March 15, 1955, Michele Besso died. Einstein's closest friend from the old days, the same Besso who had worked beside him at the patent office, the same Besso acknowledged in the only footnote of the 1905 paper. They had been friends for over 50 years. Einstein wrote a letter to Besso's family on March 21st, 1955. He was 76 years old and in declining health. He had an abdominal aortic aneurysm that was slowly enlarging. He had less than a month to live. He died on April 18th. In the letter, after the condolences, Einstein wrote, "Now he has departed from this strange world, a little ahead of me. That signifies nothing. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. Not might be, not can be interpreted as, not in certain mathematical formulations appears to be, is." Rovelli has cautioned against reading too much into this. It was a condolence letter, he notes, not a physics paper. Perhaps Einstein was offering comfort, not metaphysics. Perhaps Besso is not really gone because time is not real, was a physicist's version of he is in a better place. But Einstein's published scientific writings say the same thing. In his 1916 popular book, he wrote that it is more natural to think of physical reality as a four-dimensional existence than as the evolution of a three-dimensional one. And in 1949, his friend Kurt Godel made the case explicit. Godel, the greatest logician since Aristotle, the man who proved in 1931 that any consistent mathematical system complex enough to contain arithmetic must contain statements that are true but unprovable, a result that shattered the foundations of mathematics and ended the dream of a complete, self-contained, formal system. In 1949, he turned his attention to time, and what he found was equally devastating. He published 2 works that year, both of which Einstein read carefully. In Reviews of Modern Physics, he presented a solution to Einstein's own field equations, describing a rotating universe that contains closed time-like curves. These are paths through space-time that loop back on themselves, literally returning to their starting point in both space and time. In Godel's universe, you could board a rocket, fly in a sufficiently large circle, and arrive back at the moment you departed. Travel to the past is not just permitted, but required by the geometry. This alone would have been a landmark result. But Godel was not primarily interested in time travel. He was interested in what his solution said about the nature of time itself. In the companion essay published in the Schilp volume, Albert Einstein, philosopher-scientist, Godel drew the philosophical conclusion. He wrote that following the consequences of relativity theory yields an unequivocal proof for the view of those philosophers who, like Parmenides, Kant, and the modern idealists, deny the objectivity of change and consider change as an illusion or an appearance due to our special mode of perception. Unequivocal proof, not suggestive evidence or a possible interpretation. Godel, the most precise thinker alive, chose the words unequivocal proof. Godel also wrote, "Each observer has his own set of no's, and none of these various systems of layers can claim the prerogative of representing the objective lapse of time." His argument was elegant and devastating. In his rotating universe, there is no global time order. Events that are in your future along one path through space-time are in your past along another path. The concept of before and after becomes path-dependent, like the concept of uphill and downhill on a closed loop. There is no objective direction. There is no objective flow. Now, our universe, as far as we can tell, does not rotate. We do not live in Godel's specific solution. And Einstein raised this objection in his reply, noting that Godel's solution seemed physically unrealistic. But Godel's deeper point was more subtle than we live in a rotating universe. His argument was this: the laws of physics are the same in every solution of Einstein's equations. His rotating universe obeys the same field equations as ours. If time were a genuine, fundamental feature of reality, it should appear in all solutions, not just some. The fact that there exists a solution in which time demonstrably does not flow means that time cannot be a fundamental feature of the theory. It must be an emergent, contingent, solution-dependent feature. And if it is not fundamental in the theory, it is not fundamental in reality, because the theory is our best description of reality. Einstein accepted Godel's argument. In his reply in the Schilp volume, he raised some concerns about the physical plausibility of the rotating solution, but he did not dispute the philosophical conclusion. He did not argue that time flows. He did not defend the reality of now. He accepted what his own equations, in the hands of the world's greatest logician, were telling him. According to reports, Godel would periodically ask visiting astronomers whether observations had yet confirmed that the universe rotates. He was always told no, but his argument was more subtle than requiring our universe to be his universe. His point was, if the laws of physics permit a universe without objective time, and our universe obeys those same laws, then time cannot be a fundamental feature of reality, even in our universe. The laws do not care which solution they happen to describe. If time is real in ours, it should be real in every solution. But in Godel's solution, it clearly is not. And that argument has not been answered. I want to stay with this for a moment, because I think the free will implication is the one that explains why the block universe stays out of popular science communication, and it is the one that physicists are most reluctant to discuss publicly. If the block universe is real, the future already exists. Your future already exists. The decision you are about to make, whether to keep watching this video or click away, already exists as a fixed point in the four-dimensional block. You will experience the sensation of choosing. You will feel as though you are weighing options, deliberating, exercising agency, but the outcome is already there. It was always there. The sensation of choosing is a feature of how your brain processes the block, not evidence that the block is incomplete. David Kyle Johnson, a philosopher at King's College in Pennsylvania, put it plainly in 22:3. If what I will do exists before I even do it, it does not seem I freely choose to do what I do. When I think I am freely choosing, I think that both doing and not doing some action are both genuine, actual, real possibilities. If only one is possible, it is not within my power to choose otherwise. Brian Greene said it even more directly. Although you feel as if you have control over your actions, the laws of physics are really pulling the strings. Now, the dominant position in academic philosophy is compatibilism, which holds that free will is compatible with determinism. Because free should be understood to mean acting according to your own desires and reasoning, without external coercion, rather than could have genuinely done otherwise. This is a respectable position. A majority of professional philosophers endorse some version of it, and I understand why it is appealing. It lets you keep moral responsibility, legal accountability, personal agency, and human meaning intact, even in a deterministic universe. But I want to be honest about something. It has always struck me as a position that was designed specifically to let you keep believing in free will. After the physics has taken it away, it answers the question, are my decisions free, by redefining free, until the answer is yes. This is a move you can make in philosophy. You are allowed to redefine terms, but it does not address the visceral horror of the original question, which is, does the moment of my death already exist right now in the same way the moment of my birth exists? And the block universe says yes. Compatibilism does not dispute this. It just argues that you should not find it threatening to your concept of freedom. I find it threatening. The physicist Jim Al-Khalili has identified 4 logical options. First, determinism is true and there is no free will. Second, determinism is true, but free will survives through compatibilism. Third, determinism is false, perhaps because quantum randomness introduces genuine indeterminacy, and this somehow allows free will. Fourth, determinism is false, but quantum randomness does not help, because randomness is not the same as control. You are no more free if your decisions are determined by the roll of a quantum die than if they are determined by prior causes. Al-Khalili personally leans toward a version where chaos theory provides the escape hatch. Even in a deterministic universe, he argues, the future is only predetermined if you could calculate it from initial conditions, and chaotic systems make this practically impossible, even in principle. The block universe may be complete, but it is only knowable from the outside. From the inside, the future is effectively unpredictable, and that unpredictability may be functionally equivalent to freedom. I am not sure that works, but I respect the attempt. A 2025 paper on Arxiv goes further, arguing that there is actually no good evidence that physical determinism accurately describes our universe. Quantum mechanics, they argue, introduces genuine ontological indeterminacy, not just epistemic uncertainty. If the future is genuinely not determined at the quantum level, then the block universe may be incomplete. The future may truly be open. This is one of the live edges of the debate. If quantum mechanics is fundamentally indeterministic, and if that indeterminacy is real and not just a feature of our ignorance, then perhaps the block is not fully formed. Perhaps it is being written as the quantum coin flips resolve. George Ellis's evolving block universe captures this intuition. The block grows, accreting new moments as quantum events crystallize into classical outcomes. But here is the thing. Special relativity does not care about quantum mechanics. The Riedt-Dijk-Putnam argument does not invoke quantum mechanics. The relativity of simultaneity does not require quantum mechanics, and the experimental confirmations of time dilation operate entirely within the classical regime. Whatever quantum mechanics eventually says about the openness of the future, it will have to be reconciled with the fact that special relativity, as currently confirmed, does not provide a universal now for that openness to be anchored to. The deepest question remains, if you are a static pattern in 4 dimensions, why do you experience anything? Why is there something it is like to be a braid in spacetime? The neuroscientist Dean Buonamano at UCLA proposed in his 2017 book, Your Brain is a Time Machine, that the answer may lie entirely in neuroscience rather than physics. The brain evolved internal clocks, neural oscillators, temporal processing mechanisms, that create the subjective experience of time flowing. The block universe may be physically correct, while the experience of temporal flow is simply what brains do. The way color is what brains do when processing electromagnetic wavelengths. Color does not exist in the physics, only wavelengths. Your brain adds the experience of redness, of blueness. Maybe your brain adds the experience of flow. But this answer is circular in a way that should bother you. Who is the brain adding the experience for? If you are a static four-dimensional pattern and your brain is part of that pattern, then the brain that adds the experience of flow is also static. The addition has already been added. The experience has already been experienced. Every moment of your subjective awareness, from birth to death, exists simultaneously in the block. There is no process of adding, because processes require time, and time is what we are trying to explain. Let me bring this back to the experiments, because the experiments are what separate this from philosophical speculation. And the experiments are not slowing down, they are accelerating. Each new result tightens the noose on any escape route from the block universe. The calculations have been checked, the clocks have been flown, the muons have been counted, the strontium atoms have been measured across a millimeter, and in 2004, the LHAA-SOA collaboration performed what may be the most consequential null result in recent physics. On October 9th, 2022, a gamma-ray burst designated GRB 221009A was detected by multiple observatories. It was the brightest gamma-ray burst ever recorded, so energetic that it temporarily disrupted Earth's ionosphere from a source roughly 2 billion light-years away. The LAASO detector in China's Sichuan province captured photons from this burst, spanning an enormous energy range. And the collaboration used those photons to perform a simple but devastating test. Do photons of different energies travel at slightly different speeds? This matters because if the speed of light varies with energy, even by an inconceivably tiny amount, it would mean that Lorentz invariance, the mathematical symmetry underlying special relativity, is not exact. It would be approximate. And if it is approximate, then there might be some deeper framework at higher energies where time becomes absolute again, where now is restored, where the block universe is merely an artifact of the low-energy approximation, rather than a fundamental feature of reality. This is the escape hatch. If Lorentz invariance breaks, the block might crack. They found no variation, none. The constraint they placed on the energy scale of potential Lorentz violations was 10 times the Planck energy. The Planck energy is the scale at which quantum gravity is expected to become relevant, roughly 10 to the 19th giga-electron-volts, the highest energy scale that has any meaning in our current understanding of physics. And the LAASSO result pushed the bound to 10 times beyond even that. Published in Physical Review Letters, Volume 133, the escape hatch is not just closed, it has been welded shut. I want to be precise about what this means and what it does not mean. It does not prove the block universe is correct. You cannot prove a philosophical interpretation with a null result in a physics experiment. What it proves is that the theory from which the block universe interpretation flows, special relativity, is correct to a degree of precision that approaches the limits of what physics can currently describe. If there is a deeper theory that restores the flow of time, that makes the present moment objectively special, that gives you back the open future you feel you inhabit, That theory operates at an energy scale beyond anything we have tested, possibly beyond anything we could ever test. It is not just hidden. It is hidden behind a wall that may be permanently impenetrable. And the experiments keep coming. NIST has plans to drive an optical lattice clock to the summit of Mount Blue Sky in Colorado at 4,348 meters, for comparison with a laboratory clock at lower altitude. 2 high-performance optical clocks are planned for installation on the International Space Station, which would enable tests of gravitational time dilation 50 times more stringent than any previous measurement. The 2022 GIAL result, measuring time dilation across 1 millimeter, is being pushed to the sub-millimeter scale. Each new experiment adds another decimal place to the confirmation. Each decimal place makes the escape harder. In the meantime, the theory we have, the one that works, the one that has never failed a single experimental test in 120 years, the one that runs the GPS in your phone and predicts the lifetime of every muon ever measured and corrects the clocks on every satellite in orbit and describes the geometry of every gravitational lens and every binary pulsar and every cosmological observation, says that time does not flow. And here is where I want to close the circle, because this story starts and ends with the same man in the same city, separated by 50 years of consequences that he understood from the beginning. In 1905, Albert Einstein was 26 years old, earning 3,500 Swiss francs a year at the patent office in Bern, with a 1-year-old son and a wife, and no prospect of an academic career. He had been rejected by every university he had applied to. His former mathematics professor called him a lazy dog. He had no laboratory, no funding, no colleagues, no institutional support of any kind. And he wrote a 30-page paper with 0 references that destroyed absolute time, abolished universal simultaneity, and implied that the future already exists. The paper was ignored for 6 months. When people finally read it, they struggled to absorb the implications. Minkowski formalized those implications as 4-dimensional geometry, and Einstein called it superfluous. And then Minkowski died before he could see his framework become the foundation of all modern physics. The Nobel Committee, hamstrung by an ophthalmologist who could not follow the mathematics, and a political climate that labeled the theory Jewish physics, refused to honor the work and threw an unprecedented disclaimer into the prize citation to make sure everyone knew they were not endorsing it. Bergson, the most famous philosopher in Europe, stood up in Paris and asked whether physics had the right to declare the experienced present moment an illusion, and Einstein dismissed the entire philosophical tradition in a single sentence. Godel, walking with Einstein through the streets of Princeton in the late 1940s, proved that Einstein's own equations permit a universe without time, and Einstein accepted the conclusion. And then, in March 1955, when Michel Besso died, Einstein wrote to Besso's family the sentence that captures everything. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. He died 28 days later. The aneurysm ruptured on April 13th. He refused surgery. He said he had done his part and it was time to go. He died in the early hours of April 18th, 1955, at Princeton Hospital. His last words were spoken in German to a night nurse who did not understand the language. Think about what he knew in that moment. If the block universe is real, and Einstein believed it was real, then he knew that his death was not an ending, not in any mystical sense, not in any afterlife sense. In a physics sense, his death was a coordinate in a four-dimensional geometry, a fixed point in the block, as permanent and as real as his birth in Ulm in 1879. The man who destroyed time knew, as he lay dying, that his death had always existed, that it was not approaching, that it was simply being reached. I do not know if that is comforting or terrifying. I have gone back and forth. Some days it feels like the most liberating idea in all of physics. The past is not gone. Everyone you have ever lost is still there, still existing, still real, just at a different coordinate. Your childhood is not a memory. It is a place. Other days, it feels like the most suffocating idea in all of physics. You are not free. You were never free. Every choice, every struggle, every moment of apparent agency was a fixed feature of a geometry that was never moving, never changing, never open to alternatives. I think this ambiguity, this unresolvability, is why the block universe has been buried for 120 years. It is not a conclusion that institutions know how to communicate. It does not fit into a lesson plan. It does not have a takeaway. It does not end with, "And that is why science is wonderful," or, "And this is what we can learn from Einstein's genius." It ends with you sitting in a room at a specific moment in your life, wondering whether the moment was chosen or fixed, whether you are a traveler or a pattern, whether the person you will be tomorrow already exists somewhere in the block, living a life you have not yet experienced, but which is, according to the equations, already real. The equations do not comfort you. They do not reassure you. They do not wrap up with a hopeful message about the ongoing march of science. They just sit there, confirmed to 21 decimal places, silent about everything except the geometry. A 26-year-old pattern clerk derived them from two postulates in a paper with 0 references. His math professor turned them into a geometry and died 4 months later. The greatest logician since Aristotle walked with him through Princeton and proved what the geometry meant. And the greatest physicist who ever lived wrote it down in a letter to a grieving family 1 month before the geometry reached its own final coordinate. You are not moving through time. You never were. You are a braid in space-time, one of the most elaborate braids known, but a braid nonetheless, and the loom finished its work a long time ago.